we've been looking at matrices, right? We've been discussing matrices pretty heavily. Um, we talked about matrix multiplication for last time, making sure that we understand that when you multiply two matrices, you can consider as when you do left side multiplication on one matrix, you can consider that as multiplying the left matrix to every column on the right matrix individually. And each of those multiplications will be the new columns of the new matrix. That's one way to think about it. We talked about the transpose of a matrix, which just means you make the rows columns into columns of rows. You switch that order of the rows and the columns of a matrix. And we only consider that to be, we can consider that a doable procedure on both square and non-square matrices. So we also talked about square and non-square matrices. We talked about the trace of a matrix, which is just adding up the main diagonals, the entries on the main diagonal, and the trace is only applicable for square matrices, which are matrices that have the same dimensions, both the same number of rows and the same number of questions. You have a homework question. What does a Z, you can email me, but just for this sake of this question, can you tell me what problem number that is? And I'll see if I can, because A transpose 2, 3. First question. Okay, so I'll help you with that. Yeah, it could be the second row, the entry in the second row, third column of the transpose of the matrix A. I think that's what they're talking about there. Let me just double check. Yeah, that's what they're meaning. They're meaning that after you find the transpose of the matrix A, find the entry of that new transpose matrix, find the entry in the second row, third column. That's what it means. All right. Does that make sense? So thank you, David. Yeah, that's what it means. Okay, then we talked about the trace of a matrix, which is just the sum of the diagonal entries. And you can only talk about the trace of a matrix if the matrix is a square matrix, which means that the number of rows equals the number of columns. So it's a square. So we talked about that. And then we started talking about what are called singular and non-singular matrices. And this new terminology, right? So we have singular matrices, which are non-invertible matrices. And we have non-singular matrices, which are invertible matrices. And what invertible means for a matrix to be invertible means that an inverse exists. And if an inverse exists, an inverse of a matrix multiplied by the matrix that we're considering gives you the identity. So that's what it means when we have an inverse of a matrix. We have really what we find is the multiplicative inverse of a matrix. So when you add them up, they give you the identity, or which means ones across the diagonal, and that's the identity matrix. And then we discussed a very particular case for the 2x2 matrix. So if we have a 2x2 matrix, so 2 rows, 2 columns, then we figured out, or we were given the formula for the, can I should write that down? I'll write that down again. So when we have, a 2x2 matrix, so the inverse, so if a 2x2 matrix A is invertible, then the inverse, and when I say A, when I mean by A, I'm saying that it has the entries A, B, C, D, right? So if I have a 2x2 matrix A and I say that the inverse exists, then the inverse is given by this formula. This is dA, this is negative B, negative C. I'm just gonna write it with these. So what you see here are the entries on the diagonal, they're switched. And the off diagonals here, they're just put negative. And we're multiplying by a scalar 1 over the product of AD minus the product of BC. And so that is my matrix. And another way people write it is D over AD minus BC, negative C over AD minus BC, negative B over AD minus BC, and then A over AD minus BC. Right, so we discussed this last time, and then we utilized the fact that once we're able to find the inverse, if an inverse does exist, right? So then in a matrix equation, so if we have a matrix equation where A is a matrix, X is the column vector equal to another column vector B, then the inverse, then the solution for X is equal to the inverse of A multiplied by, left multiplied by the column vector B. So once we're able to figure out the inverse of a matrix, then solving the system becomes very simple once we have the inverse. If we have the inverse, then we left multiply that with the column vector B on the right, and you're able to find the solution to the system. And that's the idea. Once we have the inverse, then we can solve the system. And we left off with what are called the elementary matrices, right? So when we perform Gauss-Jordan elimination upon a matrix, which means we take the matrix and we try to row reduce it until it becomes the row reduced echelon form, we're applying elementary row operations. And for every elementary row operations, we saw that we can find a matrix associated with that row operation. And essentially, when we're performing row operations upon a matrix, we can also represent that as left multiplying the matrix by an elementary matrix. And those elementary matrices are associated with the elementary row operations that we have, the 3 kinds that we have. And so the idea now, so now we have the big idea. The idea behind Gauss-Jordan elimination upon a matrix A is that we're applying elementary row operations, and there can be represented as elementary matrices. So the idea is that all of these guys here are a successive multiplication of elementary matrices. Let me just change this because N usually we use it for like the size of a matrix. So this is just like the number of steps or the number of elementary matrices. So we're applying K elementary matrices. So we're performing K elementary row operations, and K is a sum number. So we get to some number that when we do that, we reduce it, right? And if A is invertible, which is invertible, what's the idea? When we have a matrix that's invertible, right, it has an inverse. And in order for that inverse to exist, right, we have certain requirements for it. But a matrix, when you row reduce it to its row reduced echelon form, if it's invertible, produces, and this is n by n, of course, we're dealing with n by n matrices, square matrices. If we perform elementary row operations upon a square matrix A and that square matrix is invertible, then when we do all of the necessary elementary row operations, we get the identity matrix. That's the idea, right? That's what we try to do. And that's where we left off. And we saw a specific example of putting a matrix and putting it into row echelon form, not row reduced echelon form. And that's what we did so far. But before we continue with this, I just want to make something clear about the homework, right? Because in your homework, you have two things. There's a problem with where you have to find two things. You have to find what are called symmetric matrices and non-symmetric, skew symmetric, pardon me. So this is a little straightforward. As long as you have the definition, then you can do that part of the problem. So symmetric matrices are matrices with the following property. What's the property? The property is that the transpose is equal to itself. That's a symmetric matrix. So if I switch the rows and the columns and the rows, I get back the same thing. So let's look at a very simple example of that. I have one. So for example, let A equal 1, 1, negative 1, 1, 2, 0, and negative 1, 0, 5. What would be the transpose? Well, remember, the first row becomes the first column now. So let me do that. So this becomes a 1, 1, negative 1. The second row becomes the second column in the transpose, 1, 2, 0. And then lastly, I get negative 1, 0, 5. And what happens? In finding the transpose, I realize that A transpose is equal to A. So hence, A is a symmetric matrix. That's pretty straightforward, right? So in order for it to have a symmetric matrix, you can think of it as the diagonal being the point where you kind of, if this was like a piece of paper, you can like fold the matrix, make believe, on the diagonal, and you see that everything here is identical. They're the same thing. It's a reflection. It's literally like a reflection of the matrix along this diagonal. If you have if you perform a reflection on this matrix, and you get the same thing on both sides of it, then it's symmetric. And if you notice, it doesn't matter what the diagonals are. The diagonal entries are almost, it doesn't indicate whether or not a matrix is symmetric or not. So you can have anything here. But as long as this here is equal to this here matches up. If they match up with one another, then they're the same. So in general, right, we can write this in general. If you have a matrix A, Aij, this equals Aji, which is the transpose. So if when you rearrange the row, the number of row with the number of columns, when you just swap them, then and they're the same, then they are or symmetric. Then they were symmetric. So that's what it means to be symmetric, for a matrix to be symmetric. And then you have this other scenario where you have what are called skew symmetric, and these are a little similar. They're similar, but not quite the same. So skew symmetric matrices are matrices with the property when you take the transpose of a skew symmetric matrix, this equals negative of that matrix. So that's what it means to be skew symmetric. So an example of that, if I have something that looks like this, 0, 1, negative 2, -1, 0, 3, and 2, -3, 0. So if you take the transpose, what happens? When you take the transpose of this, you get 0, 1, -2, right? The rows become the columns. So the rows here become -1, 0, 3, and then 2, -3, 0. So that's the transpose. And then if you compare the matrices, the entries here with here, they're pretty much the same, right? Except that what? All the entries are just negative of one another. So then this equals indeed -a. So if you negate every entry in this matrix A, you get the transpose. So henceforth, A is skew symmetric. Hence, A is skew symmetric. Okay, any questions about skew symmetric matrices? It's just a different kind of matrix. And one thing you should notice is that for every skew symmetric, what's one thing you can notice about skew symmetric matrices that doesn't have that where this property is not necessarily true for symmetric matrices. So all symmetric matrices are what? All skew symmetric matrices have something about them. And it's something about the diagonal. I don't know if you guys see it, but hopefully, if you see this matrix here has zeros on the diagonal. Do you see how it has to be a 0? Do you see why it must be 0? The entries have zeros all along the main diagonal. Because the entries in the diagonal, right, they have to equal its negative. The only number that equals its negative is 0. There's no other number that does that. So that's why these diagonals must be 0. Or in the case of a symmetric matrix, we don't really mind what the entries in the diagonal are because it doesn't really affect the property that the entries of the transpose equals itself. It wouldn't affect it. However, for skew symmetric, the diagonals must be 0 in order for the property to hold. So that was the only thing. All right. Okay, so that's symmetric and that's skew symmetric matrices. Okay, so I want to go back to what we were discussing, that so in Gauss-Jordan, right? So the goal of Gauss-Jordan elimination for invertible matrices is to take A and perform row-reduce operations on it, right? So that it becomes I. Right? So that's what we want to do. And then what that looks like is that we take A, we apply elementary row matrices, and then we get I, right? That's the idea. So what does this become then? When you take all these elementary matrices together and combine them together, what does that product become? Does anybody see that? It becomes A inverse. That's right. This whole thing becomes A inverse. Why does it become A inverse? Because we have a matrix multiplied by, well, we have a product of matrices, which we can make that into one whole blob. So this whole thing here becomes a matrix that when you multiply it to A, gives you the identity. So then the idea is that A inverse is equal to the sum of the product of the elementary matrices. And it should follow, right? So note, every elementary matrix is invertible. That makes sense, doesn't it? So what are the elementary matrices, right? You can either have rows that are swapped. You can either have a multiple of a row added to another row, or you can multiply a scalar multiple, right? A row by a scalar. And those are elementary rows operations. And each of those row operations has a elementary matrix associated with it. And so if you swap rows 2 and 3 to undo it, you can just swap them again, right? So that's a row operation, which has an inverse. So every row operation has an inverse. You can undo it very easily because if you're adding something, you can subtract something. If you're multiplying something, you can divide. So every one of those operations has an inverse. And henceforth, every elementary matrix is also invertible. So that's important because if you had a non-invertible matrix, then this wouldn't make sense. So this inverse that we have is a product of invertible matrices, all clumped together. And so now, what is the method? So what's the method of finding the inverse? Well, one thing that we do is we take A, we find the matrix A, whatever that is, right? And then what we do is we augment the matrix with the identity. So we augment this part. And then what we do is we perform Gauss-Jordan elimination. But we're performing Gauss-Jordan elimination to the entire matrix. So the idea is that what happens? The A becomes A inverse. I mean, the A, when you row reduce it, right, becomes the identity. And when you perform, the idea is that when you perform these row operations here, you're also performing them on I, right? So this is, in a sense, there's a little I here. Because when you multiply it by the identity, you get back itself, right? So I can put this I here, I can put this 1 here. So the idea is that when I apply these row operations to A, I get I, don't I? So I'm expecting I to appear on this side of the matrix. And on the other side, the idea is that I get the inverse. The inverse pops up because when I multiply I by these indicated elementary matrices, the result gives me the inverse. And that's how we find it. So it's really not really one step because there's many steps to this Gauss-Jordan elimination. But the idea is that we make A, the matrix that we have, we row reduce it to the point that this becomes an identity. And in doing so, automatically on the right side of this divide of the matrix, I get the inverse. So that's the idea. So any questions about that? Baldwin, yes.
I just have a quick question to see if I got this down. So you want to put it in like augmented form, and then we want to
Yeah.
row reduce it?
Yes.
Okay.
Yes. So yeah, this idea of Gauss-Jordan elimination is row reduce, right? Row reduce until A is in RREF form, right? But we are assuming the assumption is that the inverse exists. So if we have an invertible matrix, right, where the inverse exists, and we perform row reduce, or when we perform Gauss-Jordan elimination, which means we row reduce that invertible matrix until it's row reduced echelon form, we're going to get the identity every time. Because remember, when we row reduce any matrix, you either get two things. You either get the identity matrix or you get a matrix that has the ones on the diagonal, but you have a row of zeros potentially.
Okay. Yeah.
Right? But the matrix, a matrix who has a row reduced echelon form that is not the identity is not invertible. And every matrix that is invertible, the row reduced echelon form of that matrix will always be the identity, will always be.
Okay.
So
Thank
to
you.
find the inverse of a matrix, we're looking at it from this perspective, right? What do we normally do to a matrix A when we put it in row reduced echelon form? We perform row operations to A, right? We just perform it. We perform row reduced echelon. We perform row operations upon A. So much so, right? So this is like, I should write this as Gauss-Jordan elimination. So again, this whole term here, Gauss-Jordan elimination, means row reduce, right? We perform row operations to A to the extent that we get the identity. Because we saw that there's a connection between row operations and elementary matrices, right? For every row operation, there exists a matrix that represents that row operation, and we call them elementary matrices. We perform a set number of them to the extent that it gives me, when I apply all of these elementary row operations to A, I get the identity. In doing so, if I were to complete that, if that's true, then the product of those elementary matrices, that product is in fact the inverse of that matrix A. And because that's the case, then to find the inverse of A, I have to perform the row operations upon the identity. And for every row operation, I have a certain elementary matrix. So if I perform all of these elementary matrices and I multiply them together, that product will indeed be the inverse. So it sounds complicated, but yet it's not. Take A, so to keep it simple, take A and augment it with the identity. Perform row operations upon it, Gauss-Jordan elimination. Perform A to make A into I, right? That's the whole point of row reduced echelon form. We take A and make it into the identity. In doing so, if I perform row operations to this entire matrix, not just A, but the entire matrix, I will get on the other side, this identity matrix will become the inverse. Does that make sense?
Yeah.
So what, let me just specify. We perform, right? We perform row operations to A, right? This matrix here, so that A becomes I. In doing so, the I on the right becomes A inverse. And this I is on the left. So row reduced echelon form ZU means invertible. No, what I'm saying is note. For every invertible matrix A, the row reduced echelon form of A will always be I. And if I call this n by n, then this will be the identity. So for every invertible matrix A, the row reduced echelon form of that invertible matrix will always result in the identity. That's for every invertible matrix. Non-invertible matrices do not have the identity as its row reduced echelon form. So that's how you distinguish between these different sets of matrices. So the group of matrices, all of them, take every matrix that's invertible. If you row reduce that matrix that's invertible to its row reduced echelon form, you will always get the identity every time. Then you have this group that's not invertible. And if you perform row reduced operations upon it to the extent that you get it into its row reduced echelon form, you will not get the identity. You would probably get zeros or maybe a host of zeros, maybe more than one row of zeros. That's the idea. But for right now, we're only dealing with matrices where the inverse does exist. And so that matrix is invertible. And so that's why this little method, this little procedure will work. It will work. It's due to this idea. The idea that when we perform row reduced echelon form and get it into its row reduced echelon form, right? We're performing matrix multiplication of elementary matrices. And that product of those elementary matrices that results in getting the identity, that product of matrices is indeed the inverse of the matrix. So let me show you what that looks like, okay? So remember what the claim was? If we have A, right? If A is A, B, C, D, right? Then what do we say? We just said this, right? I remember one student was like, wait, but how do we know that? How do we know that this is? How do we know that this is true, right? So when I gave this to you, I just said, accept it and use it, and it works. But now we can actually find it. And you'll see why this inverse is indeed the inverse. So what's the procedure, right? Procedure to find it. Procedure to find A inverse. So I already know what it looks like. I want to see if this is indeed true. So let's do it. So I want to do A is A, I, right? So the idea is put A and then augment it with I in row reduce echelon form. So that's my goal, right? So that's the goal. Okay, so then I'm going to do that. A, B, C, D, 1, 0, 0, 1. So that's the first step. That's my first step. So buckle up. It's going to be a bumpy ride from here. So from here, does anybody know what I should do first? Again, my goal is to put this in row reduced echelon form. The idea is that this matrix here becomes the identity, right? I want to make this into the identity matrix. I want to perform row operations so that this guy on the left looks like the identity. And in doing so, and in performing the row operations to the whole row, this guy will become the inverse. So what's the first step? Step number 1.
We could multiply the first row by the inverse of A.
You mean the multiplicative inverse of A?
Right.
Which would be what?
1 over A.
Correct. So I will say 1 over A, right? Row 1. This becomes row 1, correct?
Right.
And so you did that because why? Why did you do that? What's the goal to get it in row root echelon form? You want to make what?
Want to get the ones in the diagonal.
Right. You want to get the ones, the pivots, right? So then in doing so, we establish that. So this becomes 1, right? This becomes what? B over A. This becomes what? B over A, 0, right? This becomes C. This is D. This is 0. This is 1. Okay. So far, we accomplished the fact that this is now a pivot. Great. Then what's the next step? I don't want that C underneath, right? I want to clear out that C. I want to make this a 0. So then what would I have to multiply to this? So when I add it to this, it gets me 0. Negative C, right? So then I do what? I do negative C, row 1, plus row 2 gives me what? Becomes a new row. So when I do that, but you see how this becomes a little bit more like, so I know this becomes 0, but then, pardon me, when I multiply negative C to B over A, I get what? I get negative BC over A, and I'm adding that to D in the entry below. So this becomes D minus BC over A. Does everybody see that? And then I do the same thing, right? On the other side, because I'm applying to the entire row. I'm not just applying it to this row, I'm applying it to the entire row. So I'm multiplying B over A by negative C here, and I'm adding it to this. So this becomes what? Negative BC over A. This is B over A. This is 0, and this is 1. Why is this 1? Because when I multiply 0 by negative C, I get 0. 0 plus 1 is 1. So this remains 1. So far, so good, guys. So all I did was made this a 1. Boom. Clear this C out, made this a 0. Boom. So I'm done. I'm done with this column. So far, this almost looks like I, right? I just have to now take care of this guy. So this is a lot of algebra. It's not necessarily like anything out of this world. It's dealing with variables and fractions. So then now what's my next step here? Now, before we go to the next step, what I would like to do is I would like to take a note of this. So note that D minus BC over A, I can rewrite this as a single fraction. So that might be a little bit better. So in order to combine this into a single fraction, I must have the same denominator. This becomes what? AD over A, right? Minus BC over A, which is AD minus BC. You should already start to see, wait a minute. I see this AD minus BC stuff. So it didn't just pop out of nowhere, didn't it? It's part of a reason. So then what I'm going to do is I'm going to rewrite this. So rewrite as 1 B over A, 0. This becomes AD minus BC over A. And everything else is just the same. So everyone clear about that? Okay. So now we have this case here. Now what do we do? What's the next step? To make this side of the matrix, to make it an identity. Well, what do I need to do to this guy? I want to make this a 1, right? So what do I need to multiply to this to make it a 1?
You can multiply by the reciprocal.
Right. Multiply by the reciprocal, which would be what? A over?
Yeah, AD minus BC.
Right. AD minus BC. I multiply that to the second row, make that my new second row. And then when I do that, what happens? I get 1, 0. This becomes a 1. So the first row is left alone. I didn't do anything to the first row. Right. And then what happens? Then this becomes what? this becomes A over AD minus BC because I'm only multiplying 1 to it, right? Now, when I multiply it here, I have to be a little careful. A over AD minus BC multiplied by negative BC over A. What happens with the A's? They're canceled out. So then what I really have is 1, 0, B over A, 1. I think I did something here. Sorry about that. So this is B over A, right? Because by 1 over A. So this 1 should be up here. There shouldn't be a B. That's what I got. So this should be a 1 all throughout. Okay. So now we're good. So then look what I have. I got 1 over A. I got negative BC over AD minus BC. This is 0. This is A over AD minus BC. So you see how this AD minus BC business pops up in the very process of making this left matrix A into identity. And in doing so, this identity starts to form itself into the inverse of A. Okay, so now I'm here and I'm almost there, right? I'm almost there. Now, I need one more step because I need this entry above this 1 to be a 0. So how do I make this into a 0? It's only one more step. So what do I multiply to this 1? So when I add it to this guy, I get 0.
You could do -1.
Negative what?
1.
Negative 1?
Mm-hmm.
So if I multiply -1 to this B over A, I get 0.
Well, we would need to rewrite the 1.
Yeah. So what would I multiply 1 so that when I add it to B over A, I get 0?
Negative B over A.
Negative B over A, that's right. So negative B over A, if I multiply that to row 2, and then I add it to row 1 and make that my new row, what should happen? When I multiply this 1 by negative B over A, and I add it to B over A, I get 0, wouldn't I? So I completed that task. I completed the task of making the left side of that part of the matrix. I made it into the identity. So I'm done. At this stage, I'm done. But now I have to look at the algebra on the right side. So this is when you have to be a little bit more careful. So the bottom here, what happens with the bottom? Let me just see something. Sorry, there's another little thing. So because this is 1 over A the whole time, there shouldn't be a B here. It should just be without the B. So everything under here should be without the B. Because if not, yeah, so be careful with this. So there shouldn't be a B on the next one because there was no B here to begin with. So just eliminate all the B's. So it should just be a C. Okay, so I'm not changing the second row. I'm using the second row to change the first row. So the second row I can leave alone. Okay, so now what happens when I multiply this by negative B over A? So just to break it down, right? So negative B over A, I multiply it by A over AD minus BC. The A's here cancel, and I'm left with negative B over AD minus BC. And I'm taking this guy, and I'm adding it to 0. But I'm adding it to 0, so this just becomes negative B over AD minus BC. So that's what I get for that upper entry. Now let's look at the same thing with this guy. I multiply negative B over A multiplied by, so this step here is going to be a little bit more complicated. So I'm multiplying negative B over A multiplied by negative C over AD minus BC, right? And then I'm adding it to what? I'm adding this to 1 over A. So a negative times a negative is a positive, right? So this becomes BC over A multiplied by AD. Let me just change this to same color. So AD minus BC. I'm adding this to 1 over A. I have to have the same denominator, so multiply the top and bottom by AD minus BC, AD minus BC. So this becomes BC over A times AD minus BC plus AD minus BC all over A multiplied by AD minus BC. Same denominator, combined numerators. So BC plus AD minus BC. The BC's cancel, and I'm left with AD. This is A times AD minus BC, and this becomes A times AD minus BC. The A's cancel, and I'm left with D over AD minus BC. So all of this algebra that we did was simply done to show that when I take this guy, I multiply by negative B over A, and when I add it to this entry here, the result is what? D over AD minus BC. And the idea is that I have performed the necessary procedure to figure out the inverse. And this is indeed the inverse, isn't it? Indeed, A inverse is what I have there. D over AD minus BC. This is negative C over AD minus BC. This is negative B over AD minus BC. And this is A over AD minus BC. Or in other words, 1 over AD minus BC is equal times D negative B negative CA. This is indeed the inverse for a fact. So I just showed you using this procedure that I get indeed what I want. Any questions about this? Any questions about the procedure? Are we good with this? Does everybody see why the inverse for the 2 by 2 matrix is indeed the one that we started with from the beginning? So this is consistent, right? This is consistent with finding it. Okay, so let me give you another example, but this time I think we graduated to the 3 by 3 case. So so let's do one. So what if I have 1, 2, 3, 2, 5, 3, 1, 0, 8. And I want to find the inverse. So I got 1, 2, 3, 2, 5, 3, 1, 0, 8. And I have 1, 0, 0, 0, 1, 0, 0, 0, 1. So then I want to find the inverse. I'm starting with A and I in the respective places, and I want to row reduce A to its row reduced echelon form, which is the identity. And in doing so, the identity on the right side becomes the inverse. So we have to perform the row operations. So I want to clear everything, right? I want to clear everything below this one here. So what are those steps for the first one? How can I do that? Multiply row negative 2 by row 1 and then add it to row 2. Make that my new row 2. And I can also do what? Negative row 1 plus row 3 into row 3. So I'm going to do that in one step. So this becomes 1, 2, 3, right? This is 1, 0, 0. This becomes 0, 0. Then this becomes -2 is -4. This becomes a 1. Then this is a -6 plus 3 is -3. This becomes -2. This becomes 1, 0. And then in the third row, I get what? I get -2, and I get 5, and I get -1, 0, 1. Everyone in agreement so far? So all I did was I cleared the entries below 1, made them all zeros. So I already have my pivot here. This one is a pivot. This one is a pivot. So now I need to get rid of this -2. How do I do that? I multiply the second row by 2, add it to the third row, make that my new third row. And this becomes 1, 0, 0, 2, 1, 0. And this becomes 3, -3. This is 1, 0, 0, -2, 1, 0. And then what? And then you get 2 times -6 times 5 plus 5 is -1. And this becomes -4. -4 minus 1 is -5. 2 plus 0 is 2, and then I get 1. So far, so good. And then what happens with the next row, with the next step, I want to make this negate row 3, make this my new row 3. And this becomes 1, 2, 3, 0, 1, -3, 0, 0, 1. So we're in good shape, right? This becomes 5, this becomes -2, this becomes -1, -2, 1, 0, 1, 0, 0. And now I want to eliminate everything above the ones on the diagonal since I have all 3 pivots. So let me do that. So I get -3 row 1 plus row 2 into, sorry, it should be 3, into row 2. And I'm gonna have, sorry, this should be +3 to row 2 equals row 2, and this should be -3 row 3 to row 1 becomes row 1. So this becomes 1, 2, 1, 0, 0, 0, 1, 0, 0. And then I get, what do I get? This is 5, -2, -1. So for the second row, I multiply by 3. So this is 15 minus 2, I get 13. And then for the third row, -6 plus 1 is -5. And then -3, second row right there. And then I get -3 row 3. So that's -15 plus 1 is -14. +6 is that, and this becomes 3. So that's what I get so far. And then the last step is to do what? Is to take -2 row 2, add it to row 1, make that my new row 1. This becomes 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the identity. So I should finish, I'm done with that part. And this is 5, -2, -1, 13, -5, -3. And then when you multiply -2, I get -26. -26 minus 14 is -40, right? -40. And this becomes that's 10 plus 6 is 16. And then 6 plus 3 is 9. So the idea is that this is my identity, and this new matrix on the right should be the inverse. So A inverse should be -40, 16, 9, 13, -5, -3, 5, -2, -1. So any questions about this?
Professor, could you just repeat the last part?
Which one?
Like step 5, I got a bit lost there.
Step 5?
Yeah, when you were adding them up.
So second row, right? I'm multiplying the second row by -2 to add it to the first row. So this 2 here goes away. In doing so, this becomes the identity. So I'm multiplying -2 to 13. So negative 2,
Okay.
yeah, -2 times 13 is -26. When you add it to -14, you should get -40. And then -2 times -5,
Oh,
positive,
okay.
right? It's positive 10, 10 plus 6, 16. And then you get 6 plus 3 is 9. So that's what I got for the last row. And according to this procedure, this should be the identity. To make sure, you would have to
Okay.
multiply
Thank
it
you.
out.
It's just my arithmetic that was a bit wrong.
Yeah, I know the arithmetic, you've seen it. It's very easy to make mistakes with this because you have so many numbers, but of course it's just adding, multiplying numbers, but it's just several things you have to keep in mind. So just in case you just want to make sure this is right, and if you have a calculator, you can find that out. So let me show you what that looks like on the calculator. So let me share my screen. So the calculator here, we go to math, right? No, we go to second, where you see the matrix, and then you want to edit. So I want to edit. And my matrix is 3 by 3. So we got 3 by 3, not 3 by 4. And I want to change this to 1. This is 1. I got 2, 3. In the second row, 2, 5, 3, and then 1, 0, 8. Boom. So this is my matrix. And then I can find the inverse very easily. Just go back to my matrix function, press A, and then I put that -1, the indicator with the -1. And so when I press it, I should get exactly what I got, right? -40, 16, 9, 13, -5, -3, 5, -2, -1. So your calculator can be a way to immediately find what the inverse is. But now, if you don't have a calculator, you can have a sure way to figure out the inverse of any matrix, as long as the matrix does exist. But of course, when the matrix gets too big, and too big can be a certain number, it could be 10 by 10, it could become 100 by 100. This procedure actually, it becomes very inefficient. And so if you really want to study the way to efficiently find the inverse, or I should not say that, I should say, if you really want to find the efficient way to solve large systems, linear systems of equations, then you would have to learn the extension to this class, which would be numerical linear algebra, which is like a small branch of numerical analysis. And that really tells you the different algorithms, because there's several algorithms that exist in solving large systems of linear equations. So actually this way, as you scale this problem into larger and larger dimensions, this procedure in finding the inverse is actually not that efficient, because finding the inverse of really large matrices is very taxing, it's actually very computationally intensive. Even just doing 3 by 3, you see how much we sweat for this. Imagine 100 by 100. No matter, it's a lot of computations. So that there's actually simpler, more computationally efficient ways to solve it, but we're not going to be going through that. We're just doing the basics for now. So does that make sense, guys? Do you guys see how to find the inverse and the procedure? Does that make sense?
Yeah.
Yeah. So basically, we're just applying what we've learned already, and now we're just extending it to this idea of the matrix, of the inverse. Okay, so once we have the inverse, then suppose I had a system x plus 2y plus 3z equals 5. And then 2x plus 5y plus 3z equals -1. And x plus 0y, or I'm just going to write x plus 5. Was it 5? No, it was 8. 8z equals 2. So this is a system, right? 3 by 3 system. And I want to solve, right? I want to solve for x, y, and z. One way to do this is to solve groups of equations as pairs, eliminate a variable, and solve that new system. So this 3 by 3 system can be reduced to a 2 by 2 system. And I think we did that in the beginning. But now instead of doing that, what do we do instead? We write a matrix equation, right? So instead of dealing with this system as equations, we deal them as a matrix. So we have a coefficient matrix 1, 2, 3, 2, 5, 3, and 1, 0, 8. Then we have a column vector for the variables, and this equals another column vector, which are these are the numbers on the right side of the equation. And so this looks like a matrix x column vector equals b, the column vector. And so because the inverse of A is exactly what we just found, A is invertible, right? So since A is invertible, meaning that A inverse exists and we found it, then what? Then x, the solution is equal to A inverse left multiplied by B. So now this problem becomes almost a cinch. All you have to do is know how to compute matrix multiplication, right? So the inverse was what again? The inverse was this inverse here. So I got -40, 16, 9, 13, -5, -3, and 5, -2, -1. And I'm left multiplying that by 5, -1, 2. And so this will become, when I perform this matrix multiplication, this becomes my solution. And in order to save some computational time, I'm just gonna do this on the calculator. So again, you can do this on the calculator, and I'm gonna show you what that looks like. Hold on. So I'm gonna go back to the matrix, and then I'm gonna edit B. And this is a 3 by 1 matrix, so this is a column vector. And the column vector is 5, -1, 2. And then I'm going to go back to the home screen, and then I can do since I have the inverse already, I'm going to do answer, and I'm going to multiply this by my matrix B. My matrix B is right here. So when I do it, perform the matrix multiplication, the calculator knows that already. And when I multiply it, I get the column vector -198, 64, 25. So I solved it. I solved my system, linear system. very easily now because I know the calculator, how to use it, how to use matrices. And so x equals negative 198, y equals 64, and z equals 25. So when we have the inverse of matrices, if we have it at our disposal, then solving any system using that inverse is the way we solve our system now. So there are now, hopefully, things that we can now make equivalent. So we have equivalent statements, right? Equivalent statements about invertible matrices. So I remember I'm saying this, that these equivalent statements is just going to be a list of them. And we're going to go through more and more things that indicate the same thing. So first of all, if A is invertible, A is an invertible matrix, means that what? A inverse exists, right? Okay. And then what's another statement that means the same thing by saying that it's invertible? It means that what? The row reduced echelon form of A is the identity. And we say A is n by n. So if you have an n by n invertible matrix, the inverse exists. That's what it means to be invertible. Because it's invertible, the row reduced echelon form of A is the identity. What else is true? It means that the A inverse, right, is equal to the what? A product of invertible elementary matrices. Right? So the inverse matrix of A is a product of invertible elementary matrices, whatever they may be, but they exist. And since they exist, then when you multiply them out, you get the identity matrix. So far, these are the equivalent statements, and there's a bit more to that. So then the next thing is, if we have a matrix equation, right? Then, well, let me say this. If we have a homogeneous system where we have a system that all equals zeros, then what? Then X must be the trivial solution only. Keyword only. In other words, only the trivial solution exists. Now remember, what was the trivial solution? Does anybody remember that? What does it mean by the trivial solution? And again, this is a homogeneous system. We talked about this briefly. Homogeneous system is when you have a linear system and they all equal zero, all of them equal zero. And I'm saying that to solve this system, if it's homogeneous and if the matrix is invertible, then the only solution to this homogeneous system is the trivial solution. So first of all, what does it mean to be a trivial solution?
It's a solution to all homogeneous systems.
It is a solution. Very good. The trivial solution is a solution to all homogeneous systems, correct? But what is it? And I think James said it.
Zeros across the board.
Yeah, the trivial solution means that every entry is zero. So X, Y, Z, or in this case, when we generalize it, X1, X2, Xn, all of them equal zero. So when you plug in zeros to all the variables, they will always give you 0 when you multiply it out, right? That's what it means. But what it's saying here is not just that it's the trivial solution is a solution. It says that the trivial solution is the only solution. And can anybody give me a proof for that? It's not that long of a proof. There's like a little short proof. It's like really short. And one thing, when you say when you see 0 with the bar with the arrow on top, it means that's the column vector, right? So this means that the column vector x is the column vector 0. So 0 with the arrow on top is the column vector where every entry is 0. So does anybody have a proof for this? Or anybody have an idea of how to go about it? Is it like a to the negative 1? Yeah, Alexa is very much like that. Very much like that, similar to that. So if we say since ax equals 0, right? This is what we have. Then we say since a exists, right? Since a and a inverse exists, because we're assuming, right? We're assuming from part A that it's invertible. So if A is invertible and we have this homogeneous system, then we can apply A inverse on both sides of the we can apply A inverse on both sides of the equation. And since it's the inverse, this becomes the identity. So this becomes the identity times the column vector x equals the inverse times the column vector 0. But if you have any matrix and you multiply it by an entry of zeros, you're going to get that whole product become 0 again. So it becomes wiped out. And the identity times x is just x. Done. This is the proof. This is the proof. I just showed you that I solved the system, and the only scenario of that happening is that the solution has to only be the column full of zeros, which is the trivial solution, and that's it. So what I'm trying to say is that these are equivalent statements. Equivalent just means that they're the same. So if I say that A is an invertible matrix, I also mean that the row reduced echelon form of an invertible matrix is identity. I also mean that the inverse matrix of A is a product of elementary invertible matrices. I also mean when I say that if I were to have the matrix A in this matrix equation that represents a homogeneous system, then the solution can only be the trivial solution. I also mean when I say that I have an invertible matrix, I also mean that when I do have a non-homogeneous system, which means that B is not, so this is non-homogeneous, right? If something is homogeneous, then the opposite, non-homogeneous. This is when the column vector B is not the column vector 0. That's what it means. When it's not the 0 vector. Then what? Can someone complete this? Then what? Does anybody see what I can say after this? Let me just stress the fact that this means unique solution. And when I say unique, I mean one. Anybody can take a shot? No. So if AX is equal to B, then what is X going to be? If you have an invertible matrix associated with a non-homogeneous system, because the inverse exists, then we have that X is equal to A inverse B. And what's even more special about this is that this is only one solution. This idea of only one solution is very important. This is a unique solution. There's only one solution to this. So then you should start to piece things together. So you're saying, so this only works. This is only possible. To have a unique solution in a system of equations is only possible if that matrix, that coefficient matrix is invertible. If it's not invertible, then what's true? What's going to be true? If A is not invertible, then there will not be one solution. There can either be no solution or infinitely many solutions. So if A were to be non-singular, if A were to be singular, which means non-invertible, then either the scenario would be that the solution would not have a solution, it would not exist, or you have the solution that has infinitely many of them. And that's where, if you have infinitely many solutions, then the row reduced echelon form of that matrix is not the identity. It would be a matrix that has either at least one row of zeros. And then the inverse wouldn't exist. So all of this would break down the moment you say this is non-invertible. Everything would break down from here. But the moment you say this is invertible, you have all of this. All of this. Do you guys see that? So again, this list will continue. We'll get longer as we head into other things such as determinants and whatnot. But this is what invertibility means. That's why it's so important to understand what invertibility means, which again means non-singular. Okay, so this is for non-singular matrices, aka invertible matrices. Okay, great. So we know how to find the inverse of a matrix. We know the procedure to find the inverse of a matrix. We know how to solve systems of equations upon having the inverse matrix. We were able to see that now it just becomes a matrix multiplication problem, a computation to find the solution to any system, any linear system of equations, as long as the coefficient matrix is invertible. If it's not invertible, then we have to be a little bit more careful with actually solving for the solution. And now that we know what invertible matrices are, we have a list of other equivalent statements that are associated with invertible matrices, aka non-singular matrices. So let's make a little side note about when things, something about what's called consistency of matrix of linear systems. So linear algebra is full of jargon. There is a lot of terminology. Sometimes can get a little bit messy. It could get if you don't have it clear. So we have homogeneous system, and then we have non-homogeneous systems, right? So that's one way to classify linear systems. But we also have things that are called consistent linear systems and non-consistent, right? So a consistent, and I think we discussed this in the beginning, is a system that has at least one solution. Okay, so this has at least one solution. So you have systems that have a unique solution, and you have systems that have infinitely many solutions, and you have systems that have no solution. So a consistent system is a system that has at least one solution, meaning the system either has a unique solution or infinitely many. So this is under the umbrella of consistent matrix systems. So I'll give you an example. Now I'm gonna switch over, instead of using X, Y, Z all the time, I'm gonna use a different way of representing the same thing, but now I'm gonna be using X as I'm gonna use X as a symbol for variables, of course, but I'm gonna use now, attach it with a subscript. So X sub 1 is my first variable. I'm not going to be using just X anymore. X sub 1 is my first variable. X sub 2 is my second variable instead of writing Y, and X sub 3 is my third variable. Because with this, I can now make this as long as I want. The problem with having just letters, right? You can see the obvious shortcoming to that is that we only have 26 letters in the alphabet. So the moment we have a 27 by 27 system, I can't use A, B, C, D, right? And then I'll have to use a new letter for the 27th variable, but then all the other letters would have been used up already. So this way that we use subscripts for the variables circumvents that, and we don't have to worry about the number of variables. So if I want to determine the consistency, I want to determine what's a requirement for this system in particular to be consistent. So first I'm going to write out the system. Okay, so there's a lot more variables this time, right? So I have x1, x2, x3 as my variables, and then b1, b2, b3 are just they could be any numbers, but I'm calling them b1, b2, b3. So this has the form, when I write this as a matrix, right? Equation, I write this as ax with the arrow, column vector, and b, right? Where x column vector is x1, x2, x3, and the column vector b is b1, b2, b3. So how do I know, or how do I determine whether this system has a solution or not? Well, I have to kind of think of it as a matrix again. Augmented. And again, I have to perform row operations on this. So the idea is I want to write this in what? Row reduced echelon form, right? So the idea is that this here becomes, this is my A, right? So this I want to make this into row reduced echelon form A. That's my goal. In doing so, this shouldn't be too bad, right? We have negative row 1 plus row 2 becomes row 2. And negative 2 row 2 plus row 3, sorry, row 1 goes to row 3. So this becomes 1, 1, 2. This becomes 0, negative 1, negative 1. Now look what happens on the last column. B1 is here, but this becomes now what? B2 minus B1. And then the third row, this becomes 0. This becomes 0. And this becomes negative 4 plus 3 is negative 1. And this becomes negative 2. So this becomes B3 minus 2B1. Right? Okay, and then what? So I'm just making sure that I did yeah. I didn't do this correctly because I messed up on this entry here. It should be -1. Does everybody see what I'm doing? I'm eliminating, I'm making this into row reduced echelon form, right? And then what do I notice about these last two rows? What do I notice? I got the
They're the
same
same.
two entries here, right? Now, what does that indicate? When I perform row reduced echelon, when I want to get into row reduced echelon form, what's gonna happen? What's gonna happen? In the second row, right? If I want to eliminate, so first I'm gonna just rewrite this.
If I remember right, does that mean you're gonna be missing a pivot?
Yeah, I will be. So I will only have two pivots here, right? So if I have two pivots, then how many free variables do I have?
Should I have one?
I should have one. And so we'll see about that, right? So that's one thing. The second thing is if I want to make this into a +1, right? This becomes -R2 to R2. This becomes 1, 1, 2, B1. This is 0, 1, 1, and this becomes B1 minus B2 because I'm switching the signs. And then I'm just gonna do it at the same time now. I'm just gonna add now R2 plus R3 to R3. So when I add this row to this row here, I get zeros on the bottom. I have a row of zeros, but now I'm taking this guy and I'm adding it to this. And when I add this, what do I get? I get B3 minus B2 minus B1. Do you see what's happening? I'm given a general matrix system with specific coefficients. It's a 3x3 system. I want to figure out so really what I'm trying to figure out is what should these values be for B so that I get a consistent system, which means so that a solution exists, at least one of them, at least one solution exists. So either I have one solution for the system or I'm going to have infinitely many. The moment I'm performing this operation so I can get the row reduced echelon form of it, right? I get zeros in the last row, which indicates what? I get two pivots and I get one free variable. The moment I get a free variable, I have infinitely many solutions because that variable can be anything, hence the term free. It could be anything. There is no restriction to it. Do you guys see that? So I have a free variable. So two pivots, one free variable. And which one is the free variable? It's x3, right? Because this column here, I have x2, x1, but x3 is missing. So x3 is a free variable. I'll put that x3. And if I have a free variable, I have what? Infinitely many solutions. But I have to be careful about this. When do I have infinitely many solutions? What is the condition? B3 minus B2 minus B1 cannot be 0. Actually, it's the opposite of that. Suppose, you see that? Suppose that B3 minus B2 minus B1 does not equal 0. Suppose. If that doesn't equal 0, then this number here will be non-zero, correct? So if this is a non-zero number, this last row, when you write it in row reduced echelon form, says that 0 equals a non-zero number. So if this is a non-zero number, then what's the conclusion? Then what?
A solution doesn't exist.
That's right. Then this system is what? Inconsistent. Or in other words, the solution doesn't exist. So, in order for the solution to exist, what must be true? So if we have an inconsistent system, because this last number here is non-zero, which makes this an inconsistent system, meaning that the solution doesn't exist. In order to make it exist, then what must be true?
Must equal 0.
Right. So for the system to be consistent, B3 minus B2 minus B1 equals 0. Or you can say B3 is equal to B1 plus B2. So if you solve for B3, you get the sum of B1, B2. Or you can say, or B, the column vector B must be the following. It could be anything for B1. It could be anything for B2, but that last entry has to be B1 plus B2. And because I have this row of zeros, the consistent part of it means that this will have to be infinitely many solutions. It cannot be just one solution. So you start to see that we really care about two things. We care about whether a system is consistent, meaning that a solution exists, or if it doesn't exist, right? That's what we care about. So that's one thing. The second thing we care about is if it is consistent, does it have infinitely many, or is there only one unique solution? When you have one unique solution, that's associated only with invertible matrices. And this is an example of one where if you were to try to find the inverse of A, you realize, wait, it's impossible. This A that I'm given here is actually a non-invertible. And this goes back to what I said, what about non-invertible, right? Did I say something about non-invertible? I did. Yeah, I think I mentioned it in words. So I did say it in words. So when you have, like we were talking about the equivalent matrices, right? The equivalent statements. If you have an invertible matrix, that means you have what? Only one solution in any system, right? Non-homogeneous system. You only get one solution, a unique solution, if my matrix is invertible. If my matrix is not invertible, then you have either two scenarios. Either you have a system where there's no solution, it's inconsistent, or you have a system that has infinitely many solutions. But that's if your coefficient matrix is non-invertible or singular. So this matters. This idea of invertibility of matrices implies a lot about the nature of the system that we can create. So what are we doing now? We're becoming more like we're making more of an abstract. We're abstracting this idea of linear systems. I'm not giving you now a specific linear system. I'm giving you some linear system. And I'm saying, hey, dependent upon the numbers that we have as our coefficients, what must these numbers be on the right side, which is the column vector? What should these numbers be so that I do get a consistent system? And the only condition that I need is this. This is my condition. Or either one of these, right? So either this one or this one. This becomes my condition for a consistent system. If that last entry is a sum of the first two entries of my column vector, then I will always have infinitely many solutions to this. The moment that this number is not the sum of these two numbers, the moment I say what? 1, 2, and 5, I know for a fact this is no solution. If this is a 7, a 3, and a 9, 7 plus 3 is not 9. I know for a fact if I were to solve this system, I would get no solution because I already know the end goal. Like I already know the end game. I already know how this game plays out. That's why it's important. So see, all this row reduced echelon form business comes right back. So this gives us a lot of information about the system in its generality. Does that make sense? So I know I can go on and on with this. And, you know, I don't know what you guys on the other side feel, think, have to say. So please, feedback is great. If you guys don't think it's like, if you guys don't understand, what are you talking about? We're talking about systems. Like, this is the time to, you know, let me know. Yeah. So this is what's really nice about linear algebra. You start to see things from more than one angle, right? So like in the beginning of this class, you just came in, oh, linear systems, I know how to solve them, or you have an idea. But now this goes like a bit further now. Now we're dealing with, we're going to start to even go to a different dimension with when we talk about linear transformations. So that's like another level of abstraction. So we're going from very concrete examples, and then we're dealing with the matrix theory side of it. And then we're dealing with that a lot. And then we're going to go to something bigger, which are called transformations, linear transformations or mappings from different dimensions, size dimensions. So that's where like the dimensionality of things becomes important. But for now, we're just trying to make sense of matrices and how matrices are useful in solving systems. And now we're learning about systems in itself and the differences between consistent systems versus inconsistent systems. And within the umbrella of consistent systems, you have those that have only a unique solution, and you have those that have infinitely many solutions. So I want to do one more example like this that has a unique solution. So we're going to have a coefficient matrix that is invertible. So when I do row reduced echelon form, I do get the identity. So I'm going to have something like this. So x1 plus 2x2 plus 3x3. I'm going to call this B1. So again, this is just generalizing a system that has these coefficients in front of them. And I want to figure out what is what I'm figuring out is what B values, what entry should I put for the B vector so that this system exists, or like what have a unique system. So here we have x1 plus 8x3. So the question usually is this: what conditions must B1, B2, B3 satisfy so that the system is consistent? So the same thing again, right? I'm gonna have 1, 2, 3, 2, 5, 3, 1, 0, 8. And this becomes B1, B2, B3. And I think these are the same numbers that we had for this one. Same numbers. So 1, 2, 3. So see, these are the same numbers to this. So we already know that this is invertible. We already know that this is invertible. And pay attention to these numbers. We're going to come back to these numbers. Pay attention to these numbers here. 5, -1, and 2. So pay attention to what those are, okay? So we're going to do the next thing here. So we already know the end story for this. We already know that this will be the identity. But we really care about this, right? We really care about this. So let's see what happens. So in order to row reduce this, I get what? I get negative row 1 plus, sorry, -2 row 1 plus row 2 goes into row 2. And negative row 1 plus row 3 goes into row 3. So this is the left side of it is not the important part so much as the right side. So what happens here? I get B2 minus 2B1. This is B1. This becomes 5, no. This becomes -4. This is 1, and this is -6. This becomes 1, right? -6, no. -6, this becomes -3. And this becomes -2, and this becomes 5. And this becomes B3 minus B1. So that's the first step, right? We eliminate the entries below, make them zeros. And then the next step here is 2 row 2 plus row 3 becomes row 3. And this is 1, 2, 3, 0, 1, -3. This is B1. This is B2 minus 2B1. This is 0. This is 0. 2 times -3 is 6. -6 plus 5 is -1. And then this becomes 2B. So this is 2B2 minus 4B1. And I'm adding that to B3 minus B1. So I get B3 plus 2B2 minus 5B1. Right? So I'm taking the second, I'm taking the second row here, this entry, I'm multiplying this by 2, and I get this, and I'm adding this to this. So then I get this. And then what? And then I negate row 3, make that my new row 3. So this becomes 1, 0, 0, 2, 1, 0, 3, -3, 1. This becomes, so I negate all of this, right? I negate all of it. So this becomes positive, this becomes negative, negative. So I'm just going to rearrange that. This is B1, this is B2 minus B1, 2B1. This is 5B1 minus 2B2 minus B3. And then we have to do a few more things, right? We have to eliminate these guys here. So this becomes same thing we did, right? 3 row 3 plus row 2, make that row 2. And I did -3 row 3 plus row 1 becomes row 1. So again, this left side, we already know what's going to happen. It's not that interesting at this point. But now what happens is this is where things get a little fun. So I have to multiply. So I'm going to do this first, okay? So what does that look like? So I looks like what? 3R3. So I'm going to multiply 3 by 5B1 minus 2B2 minus B3. And I'm going to add that to R2, which is B2 minus 2B1. This equals 15B1 minus 6B2 minus 3B3 plus B2 minus 2B1. When I add this together, what do I get? I get 13B1 minus 5B2 minus 3B3. So I get this is 5b1 minus 2b2 minus b3. And this becomes 13b1 minus 5b2 minus 3b3. Okay, and then we're almost done here, guys. We're almost done. And then this becomes -3, right? This is -3, 5b1 minus 2b2 minus b3 plus r1, which r1 only has b1 in it. So we got -15b1 plus 6b2 plus 3b3 plus b1. This equals -14b1 plus 6b2 plus 3b3. So this here is -14b1 plus 6b2 plus 3b3. Woo, we're almost there. We're almost there. And then lastly, we got -2 row 2 plus row 1 goes into row 1. So we already know what this looks like, right? We know this is 1 0 0 0 1 0 0 0 1, which is what I wanted. I know this is 5b1 minus 2b2 minus b3. I know this is 13b1 minus 5b2 minus 3b3. And now what does the last one look like? Well, I'm multiplying -2 by 13b1 minus 5b2 minus 3b3, right? This is row 2. And I'm adding that to row 1. Well, row 1 was -14b1 plus 6b2 plus 3b3. That's what this is. And then this equals -26b1 plus 10b2 plus 6b3 minus 14b1 plus 6b2 plus 3b3. This equals what? -40b1 plus 16b2 plus 9b3. So this should be -40b1 plus 16b2 plus 9b3. What in the world did I just figure out? I figured out if I were to write this out as an equation, what did I figure out? X1 has to be -40b1 plus 16b2 plus 9b3. X2 has to be 13b1 minus 5b2 minus 3b3. And X3 will be have to be what? 5b1 minus 2b1 b2 minus b3. So what does this mean? Can anyone answer the question? What are the conditions that this must satisfy so that the system is consistent? What's the condition? So compare this with the previous example. What was the condition in the previous example in order for the system to have a solution? Wasn't this the condition? Or this one here? Like these two things are the same, right? So B1 plus B2 equals B3, right? This is the condition that must hold in order for the system to have infinitely many solutions. If you don't have this condition hold, if this is not true, then your system is no good. It's inconsistent. There is no solution. That's what we got for this one, right? There's infinitely many solutions. We knew that because our row of zeros, right? We have one free variable. Okay, now this system here is a bit different. Why is it different? because the matrix that we started with was invertible to begin with. When we do this, the identity appears. And then we have this system, we have this expression for the solution, right? The solution has to meet each of these solutions, parts of the solution has to be expressed as a linear combination of B1, B2, and B3. And my question is, what is the condition on B1, B2, B3? Can be any constant. Yes. The condition is there is none. Do you guys see why? You can literally write anything for B1, B2, B3. Anything. B1, B2, B3 could be anything. And each of these, the solutions will exist. It's just that the solutions will exist in a very specific manner, right? The moment you say this is 2, this is 5, and this is 10, x1 is defined, x2 is defined, x3 is defined immediately. But the question was, what are the conditions for these values for B? There is none. So for invertible matrices, there is no condition. It works for every B value that you choose. It works for every single one. But that only works for this invertible matrix. I tried to do the same exact thing for the other one, non-invertible. This one, there's a specific condition in order for there to be infinitely many. There's a very specific condition, and this is what it was. So this one has a condition for B1, B2, B3. For invertible matrices, there is no condition because it works for every single possible choice for B. Woo! Okay, feel good or what?